Hello students, in this lecture we'll discuss some special type of general linear groups over matrices. So for that, let us define what is general linear group of degree n. A set of all n by n matrices over reals having non-zero determinant over the set of real numbers is denoted by GL and R is also called general linear group of degree n. So we'll show that this general linear group of degree n is an abelian group. So for that, let us discuss this with a general example. Show that the set of all n by n non-singular matrices over the set of real numbers under matrix multiplication is a non-abelian group. So given is, let G set of all nth order non-singular matrices over the set of reals. Means elements of this whatever the set of matrices we have considered, the elements of the sets are real numbers and matrices are non-singular. Means the determinant of matrices are all the matrices are square matrices of order n, and all the determinant of all the matrices which we have considered in this set are non-singular. Means their determinant is non. And the binary composition given on this set is usual matrix multiplication. So our aim is to show that this algebraic structure G with binary composition multiplication of matrices is a non-abelian group. We know non-abelian because matrix multiplication is not commutative. So the set of matrices we consider that that is not commutative, therefore always a non-abelian group. So we have to show all the four properties again: closure, associative, uh, associative, identity element, existence of inversion. First property, closure, axiom or closure property. Let A and B belongs to G. Means there are two matrices belong to B. Both the matrices are of the nth order, and both matrices are non-singular, and the elements of these matrices are real. So A, B is also nth order. If you multiply two matrices, square matrices, their order remain the same. If you multiply two matrices, the resultant matrix, this also is nth order matrix, number one. Number two, if number two, the elements, if the elements of A and B are real, the elements of A is also real. So now our aim is to show that the resultant product of these two matrices, non-singular matrices, is also non-singular. So since we know that determinant product is product determinants, we have read in the properties of determinant. So now the right hand side, matrix A is non-singular, therefore determinant is non-zero. Matrix B is non-singular, determinant B is not equal to zero. And if A determinant A is a real number which is not equal to zero, determinant B which is a real number not equal to zero, the product will not equal to zero. Implies we have, if you consider any two matrices from G, their product comes out to be belongs to G. Means implies closure property holds true. Now associative property. Since matrix multiplication is always associative, so G is also associative under the matrix multiplication. So we know, we have read it, we have proved it and read it. If you multiply matrices in associative, if you take three matrices and you see A dot B dot C or A dot B dot C, the resultant comes out with C. So reciprocal holds true. Now next is existence of identity. Let I be an identity matrix of order n belongs to C. If I belongs to this G, means determinant of A is a third square matrix, yes, and the elements of I are real numbers, and determinant of A is equal to not equal to 0 because determinant of identity matrix of any order is equal to 1. This implies therefore I belongs to G. Now for all A, if if you take any matrix out of the number of matrices in G, n number of matrices in G, so I into A, antimatrix only matrix, is matrix A. Antimatrix only matrix, is matrix itself. So I into A is equal to A into I is equal to A implies I is the identity matrix of G. So existence of inverse element. Let for all A belongs to G, so A is a non-singular. That is, and is non-singular means determinant is not equal to 0. So if B is the inverse of A, B now to show inverse of A exists. Inverse of, if A is non-singular, inverse exists. Only now definition of inverse is equal to adjoint of a determinant of A. So let B is equal to, we have read in the matrices, matrix determinants. So B is equal to, let B is equal to 1 upon A determinant adjoint of A. So B is, say, B is adjoint of A is a matrix obtained after replacing the element with factors and then take transpose of that. So B is also known, B is an sort of square matrix over here. Now determinant of is real number and this is an sort of square matrix. Now this matrix, you multiply this a matrix by any real number, you multiply each entry by this A. Now taking determinant of this to the both sides. This matrix, this is matrix. So determinant of B is equal to, it's a real number, determinant of 1 upon outside, or you can multiply inside or take it. Determinant of A into determinant of adjoint of A. So determinant of adjoint of A, determinant of A into adjoint of A will show that determinant is equal to determinant of A is n minus 1 upon determinant of A. So A, we know A into adjoint for any square matrix A into adjoint of A is equal to determinant of Y is equal to adjoint of into A. You read it in the matrix determinants. So take it determinant of both sides, determinant of A is matrix, determinant of adjoint of A, determinant of A into determinant into I. If you multiply In by this real number, so each diagonal will be multiplied by A. So IA, so A into A, determinant of A is equal to determinant of identity matrix is the product diagonal entries. This is equal to, this will become A determinant of A is for n. This n order I is n matrix. You multiply this real number, multiply identity matrix of the by determinant of any real number. So you multiply each entry by determinant of A, whatever real number this is. Then determine that determinant of identity matrix In is equal to A to In is equal to diagonal entries. How many diagonal entries are there? It's nth order. A into determinant today and times repeating. Now at determinant of A into adjoint of A is equal to this. Therefore, it's a real number dividing both of a real number. Determinant of adjoint of A is equal to the adjoint of A is equal to determinant of A is for n minus 1. Substituting the value here. So determinant cancel is equal to determinant is for n minus 1. So that A is non-singular, therefore A is for n minus 1 non-singular. So this implies B belongs to G. B is non-singular. B is nth order. Now A into B, actually B is inverse of B. It's both the inverse of B. So we show B is B from the, we have read in the determinant matrix, this definition of inverse of matrix. So now we'll find the product A. A into B is equal to A into adjoint of A into adjoint of A, determinant of A into A, determinant of A into I. So substituting the value, determinant to Y, A cancels, determinant their real number, determinant cancels, and then you get A into B is equal to Y. Similarly, we can prove that B is equal to Y. Thus, for all A belongs to G, A into B is equal to B into A is equal to I identity matrix. This implies A inverse is equal to B or B inverse is equal to A. Inverse of every element in matrix. Now, since the matrix is not commutative, so G have finite number of elements. Therefore, G is n infinite. G has infinite number of elements. G has infinite number of elements. Therefore, G is a non-negative. Now, next type of special linear group of degree of. We discussed general earlier, now special. A set of all nth order square matrices over reals where whose determinant is unity. In the general we discuss whose determinant is non-zero. Now we discuss special means whose determinant is unity is called special linear group of degree n and is given by SL n. Special matrices of over reals of degree n. Now we will show that this is also a non-negative. Similar in the similar way as we did for the matrices or linear matrices of degree general linear group of degree n. Show that SL special linear group of degree n is a non-abelian group. Solution is this: given a G is a special linear set of matrices of order n over reals. That is, set of all nth order square matrices over the set of reals whose determinant is now determinant of each of the matrix of this G or SL and SL and R will be used. Now I want to show what is the composition here. Composition again is usual multiplication of matrices. So now we want to show that similar. We want to show that G with this matrix multiplication, usual matrix multiplication is a non-abelian. This structure is a non-abelian group. Like composition multiplication. Now, so similar again closure property. We have taken two matrices from G. If they belong to G, determinant of A is also 1, determinant of B is also 1. So you know productive determinants, determinant of product is product determinants, product determinant of A is 1, determinant of B is equal to 1, therefore determinant of A into B is equal to 1 implies for all AB, if you take any two matrices belongs to G, their product also belongs to G, closure property holds true. Next is, since the matrix multiplication is associative, thus associative property holds in G. You can show it. If you take A and B and C belong to G, then determinant of A into B, you can show this easier. Right? Exchange of identity there exists a unit matrix in G that is I is equal to I is equal to in such that I determinant equal to in is equal to 1. I is the answer matrix, or you can write I also, in also. For all A belongs to G, I is equal to in, because in is equal to I is equal to I, so in is equal to 1. The answer matrices, because all the matrices are 1. So for all A belongs to G, A into I is equal to I into B is equal to 1. Therefore, I belongs to ultimately belongs to G, X and X. So this I is a matrix and this 1 is a element. Now this is determinant. Now next is existence of inverse. Let for only A belongs to G, determinant is equal to 1, not equal to 0. There exists a B, same. B inverse of a definition inverse of A inverse of A gives judgment of a determinant. Belongs to G such that determinant A into B is equal to G. So determinant of B again, determinant B is equal to how much? Determinant B is equal to determinant of taking determinant both sides, determinant of A, B into this, determinant of this is equal to determinant of A, determinant of A is equal to this is equal to determinant of A is 1. Determinant of A is for n into the determinant of A. So this is equal to determinant of A is to n minus 1 upon determinant of A is for n, or you can write in a similar way as we did here. Is equal to determinant of A is equal to B is equal to this, and determinant of A is equal to 1. So 1 into 1. This is not equal to this is 1. So B is equal to also equal to both way equal to this. So this is equal to this, and determinant of 1 upon A is equal to 1. So B is equal to 1, and A into B is equal to determinant of A is equal to 1. So AB similarly AB is equal to 1 and B is equal to 1. So A B equal to B is equal to 1 implies A inverse equal to B or B inverse equal to A, which is inverse of B. Matrix multiplication is not commutative, therefore G is this G is not a Abelian group. So G is a non-Abelian group over the set of reals